Okay, section 5.5. We're going to be dealing with some integrals that aren't quite as simple as the ones that we have been doing. So it's not just a matter of knowing the basic antiderivative stuff. Okay, so we're going to work on what's called substitution. Any other more complicated things, that's where you're going to start off in Cal 2. So the idea here is that we just want to take these things and turn them into easier things, okay? So a lot of times when you see a composite function or something like that, we can trade out a piece of this function for just like another simple variable. It's just easier to run through a bunch of examples, I think, than try to describe it in words. So what you're looking for here is a part of this function where if you take the derivative of just that little piece, you see that derivative elsewhere in the function. So like what I'm talking about here is if we look at the x cubed plus 1, now not the square root part, but just the x cubed plus 1. If u equals the x cubed plus 1, and we look at the derivative of that, that's going to be 3x squared, right? And in particular, we're paying attention to the variable part because we know constants we can always factor out and stuff like that. And if you notice, we got the x squared right here beside of it, okay? And technically, I should have written the dx here because we have the x squared dx here. Now, there's a couple of ways you could kind of write this stuff out. And a lot of people like to solve this thing for dx. So du divided by 3x squared is equal to dx. Okay? So when we make these substitutions, we're just going to put a u instead of that x cubed plus 1, and the dx will be du over 3x squared. Now you notice the reason for doing this is that the x squareds will then cancel out, and we are just left with, I'm just going to pull that 1/3 here into the front, du. Now this is an integral I know how to handle because that's just the u to the 1/2. All right, so we add 1 to the exponent, so that's going to be u to the 3/2. Then we'll divide by the new exponent, and so we'll have the 1/3 times 2/3, because we're dividing by the fraction, so we multiply by its reciprocal, plus c. Okay. So that's going to be 2/9 u to the 3/2 plus c, and then we just go back and put whatever u was, and that was x cubed plus 1, yeah. X cubed plus 1 to the 3/2 plus c. And that's what our integral would be, or our antiderivative, if you want to say it that way. Okay, so let's look at another one here. We have dt over 1 minus 6t to the 4th. And again, this is a lot, you're looking for composite function stuff. It's a lot of times one of the clues. It's not by any means the only clue, but definitely one of them. So since we have this 1 minus 6t to the 4th, I'm going to say, you know what, let's let u equal the 1 minus 6t, then du would be a negative 6 dt, which is just perfect because then dt is negative du over 6, right? So now I can make my substitution, and that's going to be u to the 4th times the du over negative 6. So negative 1/6 u to the negative 4th du. And again, that turns it into the nice, easy antiderivative stuff. So negative 1/6, and we're going to have u to the negative 3rd, because be real careful on these negatives. When you add 1, negative 4 plus 1 would be negative 3, correct? So we'll divide by that, so that'll be a negative 1/3, plus our c, of course. So that'd be 1/18 u to the negative 3 plus c, and then we substitute the 1 minus 6t back in. And there's our antiderivative. Once you get used to spotting these things, it's not quite as bad as it looks at first. Okay. So how about this sucker? So here, you could think of this, if you write it out maybe a little bit differently, as cosine of theta to the 3rd times sine theta d theta. Now, if you look at this, and let me do this wrong the first way, and then kind of show you, what happens, because it's okay if you pick something wrong. You just kind of pick something else when you do it again. Okay, so let's say I try to do u equals sine of theta, then du, then du, where am I at? Is going to be cosine of theta d theta, right? If I try to make that substitution, okay, and we have d theta is going to equal du over cosine theta, that little d. Then we have du over cosine theta. Hold on, cosine cubed of theta times u times du cosine theta. But the problem is we wind up canceling one of these, so that would be cosine squared of theta, right? That doesn't help a whole lot because I still have this theta running around. I want everything in terms of u. Okay? So I don't want to have a cosine squared of u of theta times u if I can help it. Now, we can use some trig identities here if we want. Okay, so I'm going to kind of continue this on because I know from my trig identities that cosine squared plus sine squared equals 1, right? And no, that's not going to work so well. My thought didn't work that, so let's just kind of scratch that and say, you know what, u equals sine of theta was not a good way to do it, so let's scratch that, and my only other option is for u to be cosine of theta, then du would be negative sine of theta d theta. Now if I make the substitution, we get u to the 3rd, okay, and the sine of theta d theta is equal to the negative du, okay, so we'll do negative 1 times du. Sometimes I like to play a matching game instead of solving it for d theta. That's usually actually what I do. And I see sine of theta there, sine of theta d theta, and sine of theta d theta there, but it has the negative sign, so I have to put a negative in here to make up for that. So you can just kind of make that switch. We know du is equal to that. We'll put du in its place. So what do we get? Negative 1 times, do I have u to the 4th So we divide by the 4 plus c, so that's negative 1/4 times cosine of theta to the 4th plus c. And there's our antiderivative. So if you screw it up the first time and you pick the wrong thing to be u, just pick something else next time. It's not that big a deal. Okay? Now how about this? We've got sine of 2x over 1 plus cosine squared of x dx. And I mean, my choices are, we could use, and maybe you might want to try just writing down your options and seeing what happens first. We could use sine of 2x, then du would be what? 2 cosine of 2x dx. Now the problem is, I don't see a cosine of 2x in there anywhere at the moment. Okay? So maybe I would be better off having u be equal to cosine of x. But then du is negative sine of x dx, and I don't see that either. So what do? So, well, I pull up some different trig identities and see, since sines and cosines, I would like it to be sine of x or cosine of x or whatever. And if you look at some of the trig identities that we have, sine of 2 theta is 2 sine of theta cosine of theta. So let me see if we can do something with that. 2 sine of theta cosine of theta. 2 sine of theta cosine of theta over 1 plus cosine squared of theta. So I know, look, if I pick this one, all of those cosines I can put in for u, and the du does have a sine of x dx, and I should have put x's instead of thetas there. I'm sorry. And so I think that's going to be the choice that I'm going to use here. So we need a negative there, so that's going to be negative, and then the sine of x dx is equal to the du, right? Because that's what we've got right here. And then the u being cosine of x, all of the cosines of x's we can switch out for u's. Now, we've got a couple of options for what's going on here. It's not blatantly obvious what's going on, so it's not a simple antiderivative yet. I could do a substitution again, okay? Now this is where I got to start being careful, because I can continue kind of playing on, and if I would have thought about it to start with, I could have probably done this all in one big long step, but sometimes that's not easy to see. But what I'm noticing now is I'm going to use a different variable. Instead of u, I'm going to use a v. If that's 1 plus u squared, then dv would be 2u du. Okay? And then I can see that again, saying, okay, well, that would be a negative 1 dv, okay, over u. I mean over v. Sorry, v. So this is my v, right? Right here is my v. And then this part is the dv. And I know that antiderivative, 1 over something, that would be just negative natural log of that plus c. Okay. But our original thing was in x, not with that, so I'm going to take 2 steps back then and say, well, you know what? The v is really 1 plus u squared. And then the u was what? Cosine of x, correct? Yeah. Then the u was cosine of x. So this is the negative natural log absolute value of 1 plus cosine squared of x plus c. So you can repeatedly use this substitution if it helps. I could have done the 1 plus cosine squared of x being my substitution just to start off with if I had noticed that. And it would have actually been a little bit easier just to see that. What are you doing? Just to see that we have integral of, what was it? Make sure I get it all right here. Sine of 2x over 1 plus cosine squared of x. So we had this and said, okay, well, I still needed that trig identity. So that was 2 sine of x cosine of x all over 1 plus cosine squared of x. And then I could have let u equal 1 plus cosine squared of x. And then du would be, what? 2 cosine of x times sine of x dx, because we got our chain rule, right? That's supposed to be an x and a dx, because we need our chain rule for that. Now I could see, oh look, we have our du here and our u on the bottom, so that would have just been 1 over u du. And then we need a negative up here. I forgot to write the negative down, because the derivative of cosine is negative sine. And they said, oh, look, that's just negative natural log of x. And then we make the substitution, and we'd get exactly the same thing that we had for negative natural log of 1 plus cosine squared of x plus c. But sometimes it's not as easy to see, substitution like this versus something else. There's just multiple ways to do it, and you can do it repeatedly if you're careful. Okay? If you don't spot the easy way right off the bat, that's all right. You'll survive. All right, and I think that takes care of it for this one. We're going to get some more practice in the next video because we're going to be doing definite integrals with this substitution, so there will be some more examples coming up.